Having clearly established that mitochondrial defects in energy metabolism are a central factor in the development of many of these chronic disease processes, what I'd like to do now is I'd like to examine the BX protocol's novelty in restoring the metabolism of glucose and fatty acids. And we'd like to begin by describing the novel aspects of the BX energy catalyst from several perspectives. Its mechanism of action, how it's intended to actually correct the dysfunction, the clinical features involved in assessing improvements in health, ultimately leading to health restoration, because that's the goal, and the various measures that we utilize in supporting chronic conditions in general. But as a summary introduction, these are the areas that we're actually going to cover during this webcast. BX energy catalyst, its nature as a non-toxic biomolecule, its mechanism of action, some comparisons also to some of the prevailing oxidative therapies. Why is the BX superior? Why is the BX different? And finally, a model. We're going to discuss a model for clinical assessment. And this is a model focused primarily on metabolic assessment, and it's somewhat off the beaten path, but I think you'll find that interesting. BX energy, or the nature of the BX energy catalyst. Let's start there. We're talking about composition. And let me just preface this by saying that our discussion regarding the nature of the BX is based on quantum theory for the most part. So if you can just hang with me through this section, I assure you we will transition into some more concrete aspects regarding mechanisms, etc. So just hang with me here for a few minutes, if you will. So the BX energy catalyst is a highly diluted, and we're talking 10x, 12x generally, non-toxic derivative of pure crystalline fructose. That crystalline fructose is exposed to specific frequencies within a chamber. Okay? That exposure actually creates a complex of specific energy signatures that you could say kind of bind to the fructose structure in a way that we really don't even understand yet. And I understand postulating the existence of what we call this subquantum receptor within the atomic structure of the fructose sounds ethereal in nature. Doesn't necessarily imply that the particle interaction is not occurring. It's what Einstein stated. Not everything that can be counted counts, and not everything that counts can be counted, right? And I mention that because there are just some aspects regarding the BX structure, the actual mechanism, the underlying mechanism that we just don't understand. The frequency chamber, I think, is a good example. How exactly does it alter the electrostatic energy? Electronic charge density. So many of these areas we're just relying on molecular dynamics simulation or just basic theoretical calculation in order to wrap our arms around it. And I have no quandary in disclosing that, because it's not a secret that many quantum-filled theories aren't rigorously defined in the first place, simply because they're not entirely understood. And the effects of the BX, if you're talking effects, yeah, they're measurable, okay? But keep in mind, they are derived from the quantum field, where in most cases, we just really don't have a firm grasp of what's actually occurring. And admittedly, yes, this is a controversial issue, mostly because man's thinking is sometimes so myopic that they actually believe that man's omniscience is somehow complete. Scientists tend to be quite vulnerable to the temptations of arrogance. It's this sort of intellectual pride, and it's a major stumbling block. And I think we're imposing huge limitations on the scientific process when we keep insisting that definitive states must be empirically measured as to be considered definitive, and that's just wrong. That was Einstein's big complaint with quantum theory. You'll remember his famous quote, "God does not play dice." But you will likely not remember the response of a contemporary of his by the name of Niels Bohr, who responded by saying, "Einstein, stop telling God what to do." I mean, think about it. How does a physicist obtain a definitive result with regard to quantum theory? By collapsing the wave function, right? which means that the more precisely he attempts to determine an electron's momentum, the more obscure the combined effects of the atom or molecule become. So yes, he proudly arrives with a definitive answer, but at the expense of actually understanding the collective effects. It's like trying to understand a Picasso by chemically digesting the canvas. It's just not going to happen. Point is, when we're discussing specific charges in or near atoms that constitute the BX molecule, we're generally referring to that just in terms of approximation. When we're talking about charging the BX, we're simply referring to the energy that's stored in the electrostatic field of the molecule. This is not a, well, I was going to say it's not a totally foreign concept, but really it is to some extent in the realm of biophysics. This is a charging process. Yes, it's conducted in a vacuum. It involves the external application of an electrical field, but the novelty lies in the fact that this is an electrical charge that can be retained by the molecule. Okay? You stick it in the fridge for 4, 5, 6 months, and later released as this high magnitude, this high magnitude moment during transition, where the charged particle releases huge amounts of energy as it migrates toward and finally is ultimately kind of sucked up by the toxic structure. It's like a toxic structure eating dynamite at the quantum level, okay, without affecting anything else around it. And yes, it's true that the system is a function of the oscillation of the electrons, how fast the electrons are actually moving back and forth. But the actual source of the molecule's oxidation potential, if you will, is derived from what we'd call a subquantum particle field. The oscillations, the electron oscillations, are creating this, it's like a pump, this pumping effect. And out of that comes the pulsed wave. And they actually have a name for this in physics. It's called quantum superposition. And quantum superposition says we're not going to attempt to define this based strictly on electron momentum or electron oscillation, but as a collective configuration, okay, that takes into account the calculated wave function that is not something that we're going to be able to measure directly. So it's like this holistic understanding of the system. Simple version is that the BX energy catalyst induces a field, okay? And that field electrically depolarizes toxic structures. You could say that it dehydrogenates the toxic structure. You could say that it cleaves the bonds involved in the structure. But the primary mechanisms, from our perspective, at least, involve photocatalytic oxidation or photon catalytic oxidation. That's not something that we're going to be able to physically measure. It has to be perceived as a quantum state. Quick point regarding toxicity: it has none. Okay, and at 1 to a trillion, you can appreciate why. It's sugar water. Okay, and I can assure you it's a bit more complicated than that, but in reality, you're dealing with charged fructose and HPLC grade water. Yes, it took us 15 years to perfect that sugar water, so I don't want to downplay the complexity of it either, but a good compromise would be it's elegantly simple. Okay? So that's it in a nutshell, the nature of the BX energy catalyst. But let's move on. Mechanism of action. This is where we can really start to transition from the somewhat abstract to the concrete, okay, in terms of quantification of the system. So a somewhat different story in terms of the potential for actually measuring exactly what's going on. To some extent, we discussed this in the previous webcast, but when we're talking about mechanism of action, MOA, okay, within the mitochondrial landscape, a lot of possibilities here. Genetics, pathophysiological pathways, biochemical interactions, etc. So if one doesn't hone in on building a simple yet comprehensive model, then it has the potential to get out of control in short order. Okay? We've spent considerable resources on understanding the mechanism of action on both the clinical side and the in vitro side of the equation. Now, those are limited resources, but about 50% of our revenues go back into research. We'll discuss the clinical side here. The in vitro side of the equation, I think we'll have to discuss on a webcast of its own. We're studying the effects of the BX mainly on human mitochondrial energy metabolism. Most of the areas that we covered during the last webcast, including profiling the expression of 84 key genes involved in mitochondrial respiration, cell cycle, hypoxia signaling pathway, angiogenesis profiling, which will include growth factors in the receptors, chemokines, cytokines, matrix and adhesion molecules, proteases and their inhibitors, as well as transcription factors, all of which tend to be involved in chronic pathologies. But let's return to the clinical side of our general model. This is a model that doesn't look at disease per se or disease conditions in particular, but relates to universal aspects of metabolism or mitochondrial respiration. These are universal aspects that represent a common correlative feature. This is a type of clinical assessment that's really geared toward identifying the common link, if you will, in most of the chronic conditions, including autoimmune, cardiovascular, malignancies, neurodegenerative, etc. And not to appear cliche-ish, but this is the Magna Carta of our work, okay? The sort of holy grail of our scientific investigations. And I'd like to start with a comparison of BX to prevailing oxidative therapies, major autohemotherapy, H2O2 drips, could be high dose C, etc. Because interestingly enough, that's where my studies began some 18 years ago. And actually at one point, I owned a company that manufactured medical grade ozone generators, so I'm not a complete stranger to that school of thought. But it's important to differentiate the BX from other standard oxidative models like those mentioned. And we could be talking about other free radical based therapies as well, or even immune modulated reactive oxygen species, mitochondrial reactive oxygen species. The inefficacy of all of these systems could be understood under the examination of three specific defects. These are some specific shortcomings that underscore why the BX is superior. The first defects with most of the prevailing oxidative therapies that we've mentioned pertain to reduction potentials. All of the, if we're talking ozone, H2O2, high dose C, they just don't have a high enough ORP value to dehydrogenate the unsaturated proteins from filterable forms of bacteria, or even if we're talking about similar toxins, amine groups, benzene ring, that type of thing. They don't burn hot enough, is what it boils down to. And if you're in vitro in a plate, sure, you're going to see some action, but not in a bonded position in that complex 1 protein. The bond strengths just require a much higher ORP value. Superoxidation is what you really need. That's what we're really talking about. And if you doubt that, go in the lab, isolate some mitochondria, test their baseline respiration in a closed chamber if you're using something like the Seahorse or the Oxygraph 2K, and just take a baseline, then treat with H2O2 and remeasure, and you'll see what I'm talking about. You're not going to see much of a change in VO2, VCO2. And that's not to say that these therapies aren't capable of oxidizing a lot of things. I mean, there are a lot of benefits there, but we're talking about a very specific mechanism of impairment in the complex 1 protein, and it can withstand a lot of the oxidative variants, most of the oxidative variants that I've mentioned. The BX has an ORP value about 10 times higher than the average free radical carrier. The second defect that we're talking about here is polymerization. This is a major dysfunction of both the protective ROS response and oxidative therapies in general. The H2O produced biologically has the propensity to react with proteins and especially lipids in a manner that results in free radical chain polymerization. In other words, the H2O2 stabilizes, and it's just not able to burn up the toxins that are impairing electron transport. And finally, reactivity. This is the third defect. This is a major problem with most of the oxidative therapies. To some extent, this is the opposite of polymerization or stabilization. These are peroxides, not biologically produced peroxides, but peroxides that are being supplied, like an IV, for example. And the main problem here is that they tend to decompose long before they ever see the complex 1 protein. So you're seeing a systemic benefit and some intracellular benefit. No one's going to deny that, but not a corrective action with respect to mitochondrial respiration. In summarizing the deficiency with most of the peroxide therapies, we could draw on a comparison of controlled demolition. If you're attempting to implode a building from a distance, so you're placing the explosive material outside of the structure, you will likely lack the impact that you need to bring it down. Well, it's the same thing with biochemical demolition. You can't rely on an outward force. Okay? The breakdown of the structure has to occur within the toxic structure. In order to overcome polymerization and reactivity in particular, you have to light the fire from within. It has to be catalytic in nature in order for the system to have the potential to progress. One domino is not going to cascade. What we have with the BX is we have the arrangement of dominoes along the lines of the physiology itself. We're just providing that initial push or that initial spark catalytically. And I hate to break the news to you, but we're going to have to discuss energy metabolism, I think we call it the energy metabolism assessment on the next webcast, because we're out of time and I'm trying to keep these things under 20 minutes, if at all possible. Otherwise, we're going to lose people. But thank you very much for joining, and we'll talk to you soon.